Good morning, dear students. Myself, Dr. Maninder Kaur. I am Assistant Professor at DAV College, Amritsar. Today, I am going to introduce a subject of Statistical Mechanics of MSc. Now, first of all, I would like to discuss why do we need to study Statistical Mechanics. So you must have come across a term, the specific heat. And we all know that specific heat, it is defined as specific heat. It is defined as the amount of heat required to raise the temperature of 1 gram of a substance through 1 degree centigrade. Now, what do you understand from here? As you can measure that how much heat you are giving to the system. It means this is a measurable quantity. You can measure it using some appliance. So based upon this fact, this specific heat, it becomes in our statistical mechanics language, this is called macroscopic So this specific heat, it becomes, or it is characterized as a macroscopic quantity, as we can measure it with some appliance from the outside. Now, have you ever thought that why this specific heat comes into picture? So the basic origin of this specific heat, it comes from So at the microscopic level, this specific heat, it is being originated by the interaction energy between the particles of the system. But here you will wonder that you can never measure this interaction energy. So the quantities which cannot be measured using the direct appliances, they are termed as microscopic quantities. So here my specific heat is a macroscopic quantity, but the internal phenomena on which it is based, it is the interaction energy between the particles of the system, which is a microscopic quantity. And here, my dear students, the role played by statistical mechanics is huge. Now what my statistical mechanics will do, it will calculate the macroscopic properties in terms of microscopic quantities using very efficient theoretical method. So we need to study this statistical mechanics when we need to know the macroscopic quantities in terms of microscopic quantities. Now further we will discuss how this theory developed, what was its starting point, and now where presently we are standing. So next step is development of statistical mechanics. Here I am using the short form of statistical mechanics, that is SM. So all of you know, right from your 10th onwards, you come across this equation. This is what? This is a gas equation. And what does it say? It says that I take some container. It may be a cylinder. I fit it with a piston. Okay. Now this volume enclosed is my V. And if gas particles are there, Then they have some pressure P, and T is my temperature. Now temperature we can vary or we can make it constant. Here we discuss the condition where temperature is constant. So once this temperature is constant, this term it is already a constant. It means for T is equal to constant, my PV is some constant quantity. Means my P will be inversely proportional to V. So this is the observation that you are studying right from your 10th standards. And physically what it means, that if I decrease the volume, my pressure will be more, and vice versa. And this point, it was the first step towards this was the first step towards development of statistical mechanics. And it was due to the efforts of Bernoulli, Herapath and Joule. What in addition to this they found? They basically found that why this pressure is being generated. They told, or they observed, or they told that this pressure, it is due to the bombardment of particles on the walls of the container. So basically pressure is what? Pressure is a macroscopic quantity, and the bombardment of particles, that is how they are interacting with the walls of container, it is a microscopic property. So basically this was the first step towards the development of my statistical mechanics theory. Then at the next step came Crowing. He derived this equation for the pressure. Actually, we don't need to go for these derivations, because these are not in our syllabi. These are only the introduction, that how statistical mechanics got developed. Here, what my N is, this is the number density of the molecules. What is my M? This is molecular mass, and my C is molecular speeds. So now in the second step, what you can see, that now my macroscopic quantity P, it is more defined in terms of the macroscopic terms like the molecular speeds. Okay. Then at the next step, a further explanation came from Clausius. What Clausius said? Clausius said that up to this we are knowing that in a container there are gas particles, and pressure is due to the bombardment of these particles on the walls of that container. But Clausius went one step ahead. He said that when particles are moving, they strike in between themselves also. So there are intermolecular collisions also. It means if there are intermolecular collisions, then speed of the molecule cannot be a single quantity. It will be more than one speeds, or speeds are bit variable. So instead of taking a single value for molecular speed, Clausius introduced the concept of mean square root speeds. So mean square root speeds, and designated it by the symbol C bar square. So according to Clausius, P is 1/3 Nm C bar square. And actually Clausius, he is referred to as father of statistical mechanics. Okay, and next is a more interesting story than this. So after that comes So this is a very interesting phenomena actually, and interesting derivation actually, and this was a milestone in this statistical mechanics and thermodynamics. This is the Maxwell laws of distribution of molecular speeds. Now here I will give an example that have you ever thought, if you think of one pond, it is full of water. Have you ever thought that why water evaporates slowly? Why doesn't this happen that water evaporates at once? If you have answer, then it is good. If you don't have answer, then you must understand what is the Maxwell's distribution law of molecular speeds. So again in your lower classes, you must have come across this topic. Here, what is my NV? This is the number of molecules or particles having speed v, and along the x-axis we draw v. So along the x-axis v is being taken, and along the y-axis number of particles which are having these velocities is being taken, and the curve is like this. You have many times come across this curve. Now, what is the significance of this curve? This curve. Now, if I take point here on this curve and I make intercept or perpendicular on the y-axis as well as on the x-axis, then what this will give me? This will give me, this point will give me the how many number of particles are having velocity, which is given by this mark. Okay, and what we can see that this point, it depicts small velocities, that velocities which are smaller in magnitude, and number of particles that have smaller magnitude velocities is very less. Now the most interesting part of this curve is this peak. Now I take point on this peak, again intercept over here, this point and this point. This point tells me that maximum number of particles, they are having a particular speed, and that is the speed that you are often referring to the most probable speed. So in our system, that is, if I am looking at the pond, everything seems to be very quiet, everything seems to be equal, but inside it nothing is equal. There are many or maximum number of particles which are moving with a single speed, that is called the most probable speed. There are few number of particles which are having speeds less than most probable speed. Now let us come to this tail. I take a point over here in this tail, again and intercept on the y-axis, intercept on the x-axis. Then here again I find that actually this intercept gives me that it's a large velocity, but here on the y-axis I find that number of particles is small. So in the nutshell, what is going on, that there are only few particles which are moving with smaller velocities, and there are again very few particles which are moving with very large velocities. Maximum of the particles, they are moving with the speeds which are called as the most probable speed. Now here lies the question that I have asked you at the starting of this Maxwell-Boltzmann distribution of molecular speeds. The answer is that not all the particles are evaporating. Why? Because the particles which are having speeds or which are at the tail, because they are having the maximum speeds, only they will get the sufficient energy to evaporate. So only few number of particles they can evaporate, not all. So slowly the particles, as they are gaining, as they are coming into this tail, they are evaporating and so on. So this was this Maxwell's distribution law of molecular speeds. It was a wonderful thing that was discovered in this statistical mechanics. So ahead of this is the H theorem. What is H theorem? Now if you take a cup of hot water, you keep it for some time. What do you observe? You observe that after some time it loses its temperature, it loses the heat to environment, and environment and the water, they come into the same temperature level. This means that what nature prefer? Nature prefers equilibrium of the system, and this H theorem explains the tendency of natural systems to attain and stay in the state of equilibrium. Further, next step was so the further step to this development of this statistical mechanics is the Boltzmann transport equation. Now as the name is depicting, it is a transport equation. With this equation we can very well explain the conduction, heat conduction of the metals, electric conduction of metals, and such transport phenomena, that where the system or the particles are moving from one end to the other in our circuit or in the conductor whatsoever we are taking. So the Boltzmann transport equation, again this is a wonderful equation, and it explains many of the phenomena like heat conduction and the electric conduction and many more. And side by side, what was going on? Side by side, quantum mechanics was developing. So quantum mechanics was developing, and what quantum mechanical had established till that time, that if we take particle for example an electron, my quantum mechanical till then said that this electron, it can behave both as a particle as well as a wave. This is called as the dual nature of the particles. Similarly, if we take photon, it can also behave as a particle as well as a wave. Now in our statistical mechanics, for the purpose of our explanation, we will focus on this photon. So if this photon is acting as a wave, so it, now two waves, they are mostly indistinguishable. So here I will tell you some comparison of classical and quantum mechanics. I say that if I have two particles or two waves, in my classical mechanics, what is there, that they are always distinguishable, because we can distinguish these two particles from the trajectories they are following. But what happens in case of a wave, that since wave has a certain spread, so even if distinguished particles are traveling like waves, then they will get mixed and they lose their distinguishability. So according to this, my photon, it must be treated as indistinguishable particle. Now, to include this indistinguishability of particles, Bose-Einstein statistical mechanics was developed, and side by side it was established that electrons are Fermi particles and not that is a single state. It can be occupied only with a single electron with all the quantum numbers same. So there was Pauli exclusion principle. So for the Fermi particles, we must consider this Pauli exclusion principle also. So to inculcate this, we that is the first step of this statistical mechanics was Fermi-Dirac statistics. So Bose-Einstein statistics and Fermi-Dirac statistics. And at the last step, what is there, that now from here that the quantum behavior or the wave behavior has creeped into our statistical mechanics. This means we must have a quantum version of our statistical mechanics. So at the end where we are now standing is the quantum version of statistical mechanics, and in parallel to our quantum mechanics, this whole description is based upon the density matrix formulation. So this was all about the today's lecture, that here we have only understood that why we need statistical mechanics and how this statistical mechanics has evolved, starting from our simple law PV is equal to nRT up to the quantum version of density matrix. Thank you all.